Okay, so welcome everyone to the third episode of season 8 of the Isogeny Club. Today we have Harun giving us a talk. He is a postdoc at the ENS Lyon, and he will talk about the expansion properties of the supersingular isogeny graph with level structure. So please take it away, Harun.
Absolutely. Thank you so much, Jonathan, for the intro, and thank you so much for the invitation. It's really great to be here. I'm excited to be sharing this with you all. The title of my talk is Expansion Properties of the Superspecial Isogeny Graph with Level Structure. And so the main focus will be in this talk be stating some parts of the main results in our current joint work with Maria, Olivia, and Benjamin. I will try to give some parts of this main results in more understandable way, hopefully. First, I will try to give motivation, especially by reminding what was the supersingular isogeny graph. In this way, I will have chance to remind you some basic geometric and graph theoretical concepts that would be useful for later. And I will try to give the main object, which is the superspecial isogeny graph in a parallel way to the graph for one-dimensional case. Since this is an Isogeny Club, I should say something about isogeny-based cryptography. I think, first of all, the dimension one isogeny problem underlies the secret of most of the isogeny-based cryptography. And we know that theoretically, the isogeny problem can be seen as a path-finding problem in the relevant corresponding isogeny graph, which is called l-isogeny graph. And then one can try to understand the hardness of these fundamental questions, trying to understand the expansion properties of this graph, because it helps us about analyzing this hardness. And then this is related to secret of our works. And so the main focus of my talk is looking at the similar expansion properties in higher dimensions. One reason I can motivate you by saying that because the understanding higher dimensional isogenies is also significant for navigating this per singular isogeny graph in dimension one. And we know lots of things about the properties of the one-dimensional isogeny graph, but comparatively, we know little about the higher dimensional graph, except the very recent last works. So let's define what was the supersingular isogeny graph. I will start fixing two distinct primes, L and P. Most of the time, P denotes the characteristic of my base field. L will denote the degree of my isogenes. This supersingular L isogeny graph, I will use the notation G sub L, but I also want to say this is GLP1 to denote later my general notation for higher dimensional. For now, just it is G sub L. If you want to define a graph, you have to at least describe two things, vertices and edges. The vertices in this graph are supersingular elliptic curves, optisomorphism. And the edges are basically isogenies up to some equivalence classes. More precisely, if you take two vertices in your graph, E1 and E2, they are supersingular elliptic curves. The edges from E1 to E2 are all L isogenies up to postcomposition by automorphism of the target, which is E2. By definition, we can state the number of edges from E1 to E2. It is the number of l-isogenes quotient, the cardinality, the number of the automorphism group of your target. For different reasons, I will give the definition of edges in terms of groups, because I will do this for higher dimensional case as well. Equivalently, I can define my edges. There are many edges from E1 to E2 if there exist n distinct subgroups of L torsion points of your elliptic curve of order L, such that the quotient of this group with your elliptic curve is your target curve. Now let's start to talk about the properties of graph. In this way, I will implicitly define some terminologies like connected, like regular, Ramanujan, etc. First of all, it is well known supersingular l-isogeny graph is connected, meaning that if you take any two vertices, you can always find a path from your vertex V1 to V2. This means that you can always find an L power isogenes from V1 to V2. Also, it is regular, meaning that the number of edges from one vertex to the other vertex is always the same number. In this graph, it is L plus 1. You can see this just by counting the cyclic subgroups of order L. And it is finite group. It means that there are around P over 12 many supersingular elliptic curves over our base field of isomorphism. And there is one more closely related to the title of our talk, a nice property with this Ramanujan property. To define this and to mention this, I want to order my vertices. Since we are talking about a finite graph, say we have n many vertices from V1 to Vn, and then we can associate a matrix which lives in n by n, matrix set with the integer entries. This is called adjacency matrix. This really keeps lots of useful information about the graph. And this matrix has the entries like the number of edges. For example, the first entry will have the number of edges from V1 to V1 and etc. And the spectral radius will be about the largest eigenvalue. More precisely, if lambda is an eigenvalue of our matrix, adjacency matrix, we will say the absolute value of lambda is degree of our graph. This is trivial eigenvalue. And we will keep the information, which is the second largest absolute value among the eigenvalues, meaning that it is the maximum of the absolute value of lambda. Lambda varies over non-trivial eigenvalues. I put a small parenthetic comment if it exists. It's a very small point. I don't want to confuse, but if it doesn't exist, just define it is 0, or it depends your convention. You can define in a similar way. And then the Ramanujan property is indeed your spectral radius lambda of G is less than or equal to 2 times square root of degree of your graph minus 1. Recall that the l-isogeny graph was L plus 1 regular graph, so the degree of your degree of L supersingular isogeny graph was L plus 1. So the Ramanujan property says if your spectral radius is less than or equal to 2 plus square root of L, the L supersingular isogeny graph is Ramanujan. And Pfizer proved that this is the case. So this L isogeny graph is Ramanujan. But I defined explicitly what Ramanujan means. But what does it mean really? I mean, for example, for crypto, the random walks are really useful in isogeny-based crypto. And being a Ramanujan means it is perfectly connected, it is well connected, it is well distributed as theoretically possible. I mean, the random walks have rapid mixed properties, meaning that the target of a random walk of enough length is indistinguishable from a uniformly random vertex. This is highly, in practice, useful property. This is the main point. This will be a main point, for example, in the applications I will present at the end of this talk. Okay. Until now, I only discussed the l-isogeny graph without level structure or extra data. Now, I want to put some extra data for each vertices, which is a finite set. And then, of course, I will ask some compatibility for my l-isogenes. For this, start fixing a capital integer n, which is co-prime to p times l. And then to define a graph, again, I will define my vertices and then edges. The vertices are pairs, E and P. E is my supersingular elliptic curve as in the l-isogeny graph. And P is a torsion point, which lies in the torsions and torsions of my elliptic curve. Now, the edges will be, first of all, l-isogenes from our elliptic curves, but it should preserve the torsion points. Now, I have a new graph. I will use the notation G sub L to Tor. You can consider Tor a kind of notation for functor for some reason. I will give another example. Again, I will add extra data for vertices, and then I will ask my edges some compatibility. In this case, the vertices are again pairs. One is a supersingular elliptic curve. The other is an isogeny lying in this quotient, modulo n times the endomorphism ring. And then my edges are l-isogenes. That is compatible with the endomorphisms in the edges, in the vertices, sorry, with this compatibility condition. In this way, I will have another graph, and I will use this notation for this graph. Okay. Why I am trying to add extra data for the vertices. Why I'm trying to understand this kind of graphs. I think, first of all, it is independent interest. One can just wonder what happens if we look at some graphs. This is also interesting. And even one can go further, like, for example, in the l-isogeny graphs, for any supersingular elliptic curves, we know their endomorphism rings are maximal orders, but one can wonder what happens if we want to look at the other kind of quaternionic word like Eclair orders, and there is a categorical equivalence between Eclair orders and some supersingular elliptic curves with some extra data, so one can wonder such graphs and etc. This is the independent interest. But for crypto, there is also another reason. Probably you know very well there is an equivalence of endomorphism ring problem and one endomorphism ring problem. This equivalence was shown by Errol Page and Benjamin Wesolowski. And in their proof, one of the key ingredients was to understand the equidistribution, the expanded properties of the graphs, like L-square singular graph with some extra data, like, for example, the one I mentioned in my second example. But it is important to mention that the L isogeny graph was connected, I said connected, but it doesn't mean the graphs I illustrated in two examples are still connected. They may be disconnected. There might be some trivial eigenvalues of the relevant, the associated adjacency matrices, etc. So the things are not perhaps nice as much as the l-isogeny graph. But we know that by Page and Wesolowski, actually, the core of the enriched graph remains an optimal expander. I mean, there might be some disconnected graph, but still you can somehow understand the connected components, and then you can see any connected components is actually still Ramanujan. So I can declare my aim. The aim is to investigate the higher dimensional analog of the several supersingular isogeny graphs, and the aim is to rigorously bound their spectral expansion. So the question is, of course, do these rich structural and expansion properties carry over to analog of supersingular elliptic curves? Okay, I want to define the higher dimensional analog of the objects in the one-dimensional graphs. Recall, to define a graph, we have to define vertices and edges, and in the vertices, we had supersingular elliptic curves. In the edges, we had l-isogenies. So the first step is to give the generalization of supersingular elliptic curves. And there are several ways to define the supersingular elliptic curves. It depends what really you are focusing. First of all, if you only focus that elliptic curve is one-dimensional abelian variety, you can quickly define the generalization of elliptic curve is G-dimensional abelian variety. Even you can just take the product of supersingular elliptic curves G many, and which these are a new name, which is superspecial. We say X is superspecial abelian variety if it is isomorphic to G many. But then there is a little problem, because we know that if dimension is strictly larger than 1, all superspecial abelian varieties are isomorphic. So if you can generalize your vertices in this way, you will have only one vertex. This is not reached, even this is not interesting to discuss. So there is indeed, in some sense, more correct generalization of the elliptic curves. It comes from a concept of principal polarizations, because you have only one superspecial abelian variety for higher dimensional case, but for any superspecial abelian variety, there are many principal polarizations. It is something like, for example, if you have a surface, there are some nice genus 2 curves lying on your surfaces, and these curves have some important information about your surface. So these principal polarizations have nice structural properties. And it is very different situation in the elliptic curve case, because always, not only for supersingular elliptic curve, for any elliptic curve, we have a unique principal polarization. That's why we somehow forget to mention principal polarization in that case. So anyways, the final point is that the generalization of elliptic curve is principally polarized abelian varieties. The generalization of supersingular elliptic curves is the superspecial principally polarized abelian varieties. So that's why we have to define what principal polarization is. First of all, principal polarization is an isogeny from your abelian variety to its tool. Indeed, it is an isomorphism, but this is not the definition. This is a property. The correct definition is that the principal polarization comes from some important geometric object, which is called ample invertible sheaf. This is somehow, we have an isogeny from somewhere to somewhere, but we somehow want to some positivity condition for our isogeny, not any isogeny. So the principal polarization is an isomorphism with some positivity condition. This is roughly the definition. And then we will call this pair X and lambda a principally polarized abelian variety. I will shortly say PPAV, especially if we have superspecial abelian variety. I will call X lambda as a superspecial PPAV. Now, I defined my vertices. Now I should define the edges. In the one-dimensional case, the isogenies are just isogenies for the one-dimensional objects. But now we have more structures. We have principal polarizations. So our isogenies should respect these principal polarizations as well. This means that if we have two PPAVs, the polarized isogeny, first of all, should be an isogeny between two varieties, x1 and x2, such that it respects the principal polarizations, meaning that there is an integer, there is a positive integer d such that this diagram commutes. In this case, I will call f is d isogeny because the degree of my isogeny is d2 dimension. And also, when I say degree of f, in general, I mean reduced degree. So I will call the degree of f is d. So we defined d isogenes in particular if d is a prime L. Now we have L isogenes for higher dimensional case. So we are ready to introduce the vertices and edges for the higher dimensional graphs. First of all, the G-dimensional superspecial isogeny graph is a directed multigraph with the vertices superspecial PPAVs of dimension G. And the edges are, if you take two vertices x and y, the edges from x to y are all d isogenes from x to y such that d is co-prime to p up to postcomposition by the automorphisms of the targets. This is not the superspecial l-isogeny graph, but I can immediately define the superspecial l-isogeny graph. Just I will take the subgraph of superspecial isogeny graph. I will take the same vertices, but I only allow to the edges with degree L for a prime L. Now we have the superspecial L-isogeny graph. When I define the supersingular L-isogeny graph, I use the similar definition for edges, and then I mention some equivalent definitions. I will do that here as well. First of all, by definition, we can see that the number of edges from fixed x to y is the number of L-isogenes over the number of the automorphism group of the targets. In terms of the groups, I can give another equivalent definition. For this, take two vertices again. And then there are n edges from X to Y if there exists n distinct special subgroup of the torsion group of XL, such that again we have the similar as in the elliptic curve case, X quotient G is the Y. Here I will not define what the maximal isotropic subgroups, but I can give a very quick comment. We have principal polarization. This will lead to the nice well pairings, and then we can take isotropic subgroup by looking the torsion points such that the well pairing is trivial. And maximal means really it is the maximal. But important point is that we can control, we can represent the l-isogenies in this way, and we can see that there are there's a bijection between the number of edges and the maximal isotropic subgroups, and we can see that the number of maximal isotropic subgroups can be given by the product of this. For example, if you consider dimension 2 and when L is 2, you can see there are 15 many maximally isotropic subgroup. Okay, we can start to discuss some properties of our higher dimensional graph in a parallel way to the properties of the one-dimensional. Recall the l-isogeny supersingular elliptic curve was finite. Again, this is a finite graph. And we know that the number of vertices is around P to G times G plus 1 half. And it is regular because I have already mentioned there is a bijection between the set of maximally isotropic subgroups and the number of edges. And this formula depends only L and G, which is fixed. So it is regular with the degree of this formula. And it's connected by Jordan and Zeitman. It is a recent result. But here is the problem. It is not Ramanujan. Again, Jordan and Zeitman proved that. I will mention later, but this was conjectured by some people in the crypto community, but Jordan and Zeitman show that it is not Ramanujan by giving explicit examples. Let us discuss one example. Perhaps it is surprising that the first example comes from very small values, like when L is 2, G is 2, and P is 11. Okay, now I will give why this graph is not Ramanujan. First of all, take two very usual elliptic curves like this, and take two G2 curves like this. And by using Ibikuyama-Hashimoto formula, we can see that when P is 11 and G is 2, there are 5 many principally polarized superspecial PPAVs. And then we can see that actually E1 times E1, E2 times E2, E1 times E2, and the Jacobians of these genus 2 curves are exactly represent these 5 many PPAVs. So whenever we compute the two isogenies between all these vertices, we can write our adjacency matrix. This is our adjacency matrix. For example, if you look at this column, this entry, this is 9. This means that from E2 to E2, from E1 to E1, to E2 to E2, there are 9 isogenies, polarized isogenies. So we have adjacency matrix. And it is perhaps useful to look at the sum of the entries for each row. As you see, 3 plus 9 plus 3 is 15. And if you sum up, you will always get 15 because the sum of the row will give the degree of your graph. Our graph is 15 regular. Now, the next step is to look at eigenvalues. We have eigenvalues 15. This is not surprising because we always have a trivial eigenvalue. Remember, the trivial eigenvalue was the eigenvalue such that its absolute value is the degree of your graph. And now we have 4 main eigenvalues here. Look at the largest one in absolute value, which is 7 plus square root of 3. And apply the definition of Ramanujan. It means take the maximum and compare 2 times square root of degree of your graph minus 1. But the largest eigenvalue is around 8 point something, and this quantity is around 7 point something. So the largest eigenvalue is strictly larger than this quantity, meaning that the graph is not Ramanujan. Okay, of course, this is not the end of this story because, as I said before, Ramanujan is somehow the best, like optimal expansion situation. But if you don't have a Ramanujan graph, the next question is still it has some nice expansion properties, like is it an epsilon expander, meaning that does it satisfy the largest second eigenvalue in absolute value have some upper bounds, nice upper bounds. I mean, not trivial upper bounds. If this is the situation in practice, like for crypto, this is still win. The random walks still mix fast, and the outputs quickly become indistinguishable from uniform. And this will give you some nice properties. Here is the first result about this. The upper bound for the specular radius. If I gave 2 equivalent ways to define the first main result, the L superspecial isogeny graph is epsilon expanded with this quantity. Equivalently, the specular radius have this upper bound. Recall that this is the n sub g of L is the degree of our graph. So the bound is indeed just 2 times square root of L over L plus 1 to G. But again, this is not the sharpest bound we have obtained. The better bound is in the next slides. This is the just first bound. I want to focus first this, and then I will give the better bound later. Because I want to compare these bonds with something in the literature, let's normalize our specular radius just by dividing the degree. This means that the trivial eigenvalue is always 1. So we will get, the aim is to find some eigenvalues, upper bound for the non-trivial eigenvalues less than 1. For example, there is a result. Akawa, Tanaka, and Yamachi get some bond for this quantity. The second one is their bond. And again, was our first main result. So if you compare these 2 bonds, I think it is not obvious which one is better. Also, how much their bond is good to say. We have rapid mixing properties. If we have how it is fast, etc. So that's why I want to give some very numerical data. For example, if you take the dimension 2 and 3 case and for several primes L, I calculated their bond and our bonds, and you can see, you can compare two bonds here. Perhaps there is one thing to emphasize. Their bonds somehow quickly very close to the trivial eigenvalue, which is 1. But anyways, I want to give another remark from the crypto community. Ernie Florida and Benjamin Smith actually, first of all, computed the spectral radius for two-dimensional, two isogeny graphs for several p's. It is indeed a lot p's. They computed this where p is until 600, and then they found that for this piece, the spectral radius is between these two quantities. And then, perhaps naturally, they conjectured this is the situation for any case. But if you look at our bonds, we cannot prove their conjecture. We cannot validate their conjecture yet. But here is our sharper bond. Indeed, the spectral radius has this tight upper bound, 2 over L to G half plus G L to minus G half. I am looking, is there any question? Okay, I think no. This is indeed the second main result. I call sharper bond during the talk, and I will call the first main result as a first bond. Now let's compare two bonds. This is the first bond, this is the sharper bonds. For the several dimensions and for several primes, I just calculated this. And then if you see, the second bond is really sharper than the first one. And especially if you look at this, our bond says, in this case, really we can prove Florek and Smith's conjecture. And as I said, while the first bond already established, as you see, rapid mixing, the sharper bond drops dramatically, especially for larger G and L, yielding a stronger spectral jet. Now, as I said at the beginning, I will give some parallel discussions between one-dimensional and higher dimensional case. I illustrated two examples in the one-dimensional case with extra data. Now I will do the same for the higher dimensional case. Again, start with the same capital N, which is co-prime to P times L. And then I will define vertices and edges. The vertices will be, again, pairs XP. X is a superspecial PPAV from our previous graph, as in the previous graph. And P will be a torsion point from the torsion of X of N. And the edges will be polarized l-isogenies, as in the previous graph. And I will allow l-isogenies when it preserves the torsion points. And I will use the similar notation, but at this time I will emphasize the dimension G. Perhaps I don't have to write the P, but anyways, I will write G. Again, similarly, I will define my second graph with the extra data. Again, I will have pairs X and alpha. X is a superspecial PPAV, and then I have endomorphisms in this modulo. And the edges will be polarized l-isogenies between my PPAVs, and I will allow this kind of isogenies when it is compatible with the endomorphisms. And I will use the similar notation as in the one-dimensional case. I will write the tab of G sub L and quotient N. Now I can state the similar situation as in the one-dimensional case. Even though I added some level structures, some extra data, you will see that the spectral gap is completely preserved, meaning that still the normalized spectral radius for both cases have the same upper bound. This means that adding level structure doesn't weaken the rapid mixing properties. Again, as in the one-dimensional case, your new graph perhaps not connected, perhaps have some bad things like multipartite, etc. But it doesn't matter. Our result says that still the spectral radius have the same upper bound, and also there is an explicit result. You can somehow understand the connected components and some other informations. Perhaps I should emphasize that these are just two examples to illustrate our result. In the main result, we define the extra data by using the terminology of category of elements. This idea was this method was done in the paper I mentioned in at the beginning by Ariel Pech and Benjamin Wesolowski. In their paper, they also introduced this concept to give more general framework, and then they put they just they allow for extra data of arbitrary nature, only requiring some simple property. This is the case for our result. Now I have some time to mention two applications. The first application is about the superspecial isogeny problem. In the first slide, I mentioned the role of understanding the expansion properties of l-isogeny graph for the one dimension isogeny problem. Here we can mention the similar. The problem is if you have two superspecial PPAVs, can you find an isogeny between them? Indeed, Costello and Smith gave an algorithm solving this problem, but under the heuristic that this graph, this L superspecial isogeny graph is Ramanujan. But we have already mentioned this graph is not Ramanujan, but it doesn't matter. The main idea in their approach is we just need epsilon expanded graph, not really Ramanujan graph. So by using our main result, we can give heuristic-free algorithm for this problem. The key point, perhaps I will give more words about this key point in the second application, but I can just summarize. The key point is take long enough paths of l-isogeny steps until the endpoint is somehow has smaller dimensions. I mean, meaning that non-Jacobian or split or product, which terminology you like, they are all equivalent in some sense. Then, by the main result, we can say the graph is an expander, so the random walks reach a uniform distribution fast. So we can somehow compute some probability, and then we can give the expected number of paths to have such endpoints. I will mention this a bit more in the next application. The next application is computing the endomorphism of our superspecial PPAV. First of all, the algorithm for this problem is a modification of the idea given by dimension 2 case by Annie, Bison, Ise, Garcia, and Wesolowski. The idea is, first of all, by the basis of endomorphism ring of supersingularity curve, we can find the basis of Hom E1, E2, or EI, EJ. And then we can find a basis of endomorphism of a superspecial abelian variety, because the endomorphism of this variety can be seen as a G by G matrix and matrices, and in each entry you have either endomorphism in EI or an isogeny in Hom EI, EJ. So then the perhaps important step is to take two paths, meaning that we need a path from a given X to a product of G many elliptic curves as a principally polarized abelian variety. And then we will do the same thing. We will ask a three-isogeny path in our new graph G sub 3. The first one will be alpha, the second one will be alpha prime. But what I mean finding a path to product, let's discuss this a bit more. I mean, first of all, for simplicity, suppose we are in dimension 2, but the same discussion will be valid for any dimension. And the bound in the discussion of the finite graphness, I have already said, in this case, the number of vertices is around p cube. And we know that the abelian surfaces can be seen in two distinct ways, Jacobians or non-Jacobians, meaning that we have principal polarization. Sometimes these principal polarizations are product, which corresponds to non-Jacobian case, but sometimes these are non-product, irreducible, like indecomposable. So, and we know that actually many of surfaces are indeed Jacobian. So we need to find non-Jacobians. They are comparatively less than the Jacobian ones. I mean, there are p square many non-Jacobians. But it doesn't matter, because if we take long enough paths of l-isogeny steps until the target is non-Jacobian, we can write our alpha and alpha prime. But how we know after enough steps we really can get something, because maybe the non-Jacobians are distributed very badly. But by the main result, we know that no, this is not the case, because the target of each path is uniformly distributed. This means that the probability is having split or non-Jacobian vertices is at least p over 1 over p. So if you take p many steps, you can expect what you want. Now, anyways, the second step is going from path to product, and then the third step is just combine all informations, like take beta I as a adjoint of alpha I, alpha, and similarly beta I prime. But what is the adjoint isogeny? I defined it here. Whenever you have the isogeny from your PPABs to another PPAB, you can just simply write this in terms of your principal polarizations and tool of F. This is like very roughly just tool of your map. So, and then you will see beta I and beta I prime lies in endomorphism of your X. And then the final result says that all beta I and beta I primes generate the all ring. Because it is not hard to compute the index of the ring generated by beta I and beta I prime should divide the GCD of 2 power and 3 power. But GCD of 2 power and 3 power is 1, so the index of generating this ring has index 1 in end of X, meaning that this really generates all ring. This was the second application. Okay, I will just give a little very high level words about the techniques. For the experts, I don't think the techniques is surprising because the technique is we have a discrete word of graph. We have a finite graph and we have a graph. And then we want to translate our graph to some continuous word about representation theory. Like, for example, if you take the superspecial graph, GLPG, you can translate this to a double coset of the general symplectic groups in terms of adelic language. In a similar way, if you put some extra data like Tor on end quotient by A, some level structure, you can again find some diction. You can translate this in a similar way. Like, for example, very roughly G over the adelic Z somehow keep the information of some isomorphisms, and with level structure you want some extra compatibility condition by taking the subgroup K with some properties and change the quotient. You can still keep this information and you can get some dictionary between your superspecial l-isogeny graph with level structure and these double cosets. Why it is useful? Because, first of all, what was the spectral radius of a graph, which was an eigenvalue of the adjacent matrix? But we can associate our graph to complex valued functions, and then we can define the adjacency operator on the function space. As a linear map, the adjacency operator and the adjacency matrix are the same. So if we can understand or if we can't give a bound for the eigenvalue of the adjacent matrix, we are done. And that second step is highly key step, which says that the adjacent matrix AL is the same with the Hecke operator on the space of automorphic forms. But this translates our main problem to understand the better words objects like Hecke operators. But this means that the eigenvalues of our adjacency operator and Hecke operators are equal. So if you can bound the eigenvalues of the Hecke operators, you are done. How this is possible? Because it is possible because there are, in the representation theory language, we have already some strong theorems to bound the eigenvalues of Hecke operator. First of all, the first one is Gauss bound. This is almost immediate. Like, if you set up this translation, you can immediately apply Gauss theorem and you can get our first result, the first bound. For the second bonds, you need more. You need to understand more things, which is related to Arthur's endoscopic classification. You should understand your irreducible representations well. And then to apply Arthur's bonds, you should eliminate some cases. These some cases will be related to some degenerate cases. This is good because we know in the degenerate cases we have already trivial eigenvalues. So the remaining part will be non-degenerate case, and then we can apply this theory as well. This was the last part of my talk.
Thank you very much, Harun. As always, if you guys have questions, please just unmute yourself and ask them, or type them in the chat, whatever you prefer. Oh, Arthur already has a question. So Arthur asks, sorry if I missed it, but what are the complexities you obtain at the end for finding isogeny path?
Arthur, yeah, thanks. A good question. I can't answer this question now because we still couldn't compute the complexity like carefully. It is almost done, but yeah, I can't answer now. But it's, of course, you expect it is like very bad.
For the Costello-Smith algorithm, the big O complexity is still the same though. It's like p to the g minus 1. It's just that the constants might change depending on how long the walk has to be precisely, and how long the walk has to be is still what we're figuring out. As in, like, we just have to finish the work.
Yeah. Thanks, Maria. Yeah. I think Jonathan wants to.
Yes, I have a question. Thank you. This was really nice. You mentioned that adding level structure does not weaken the mixing. It's sort of the spectral gap is still sort of bounded from below. Is it possible that adding level structure can actually increase the mixing, or is there sort of a bound that says that adding level structure can only possibly increase the second largest eigenvalue?
Okay. First of all, what I was saying is that the bound will be the same for without level structure and with level structure. That is what I really claim. And you are asking, perhaps, if I understand correctly, you are asking perhaps the spectral radius was very small without level structure, but with level structure it increases.
Yeah, I guess just in general, like, is there anything at all we can say about the relative sizes of the spectral gaps for with or without level structure?
I think, yeah, I understood. I think no, because it may depend on which kind of level structures, but I think what I see sometimes, not always, we can really get the copies of the graphs. I mean, without level structure, we have a graph with some properties. With level structures, we are getting, like, say, a graph with 5 connected components. Each connected component may look like the one with does it make sense? But I'm not saying this is always case.
Yeah.
Because but we have something to analyze this. We didn't analyze this for each cases, but by using our results, I think one can analyze.
Like, that's interesting. Thank you.
Yeah. For example, where it perhaps in some sense trivial, but I gave you an example about the level structure torsion points. When you checked our results, we somehow control the number of connected components by some orbits. You can see there is only one orbit. So then you can see, it is connected. And then by looking at these orbits, the stabilizer groups, you can see, all of them are the same graphs, etc. Yeah.
Well, thank you.
Yeah, welcome.
Okay, maybe I can also ask. It's a bit related to like the previous question by Arthur, but maybe a bit more basic, or maybe I misunderstood, and this is exactly the question. But like for an epsilon expander, how like what is the how long of a walk do you have to take to be uniformly random?
Yeah, that's a good question. Even though I was expecting such questions, of course I should prepare answers. But it requires a little more works.
Okay.
We really should do sometime. But Maria, do you have any answer for this? Roughly.
It's some constant times log p, and this constant will depend on the bound and the eigenvalue you can get, and so
Yeah.
we just don't have that constant yet.
Okay. I guess it was essentially the same question as before. Sorry.
No, I mean, it's a good question, and it's definitely a result that we will add. It's just we haven't. Yeah, it's still ongoing. And so now with this result on the eigenvalue, we can figure out the length of the walk. But we know that it's because it's expander that it will be some constant times log p, where the constant is not too big. It will be something like less than 10, I assume.
Okay, nice.
Yeah, I can't say.
And it's not a big number, so that's.
And I guess maybe it will depend on the dimension, actually. But yeah. Sorry, Mark, go ahead.
Yeah, no worries. Sorry for interrupting your answer. So I have an even stupider question, which is about this definition of expander graphs, because you're saying the second largest eigenvalue is at most 1 minus epsilon times the largest one. Is that the definition?
Yes. 1 minus epsilon. This is the definition. 1 minus.
Yeah, and n is the largest one.
No, n is the degree.
Okay, so wait, what is the largest eigenvalue then?
Lambda g. Lambda g is the spectral radius, like meaning the second largest eigenvalue in absolute value. I mean, if you take n here, in the left you will get the normalized spectral radius. So the epsilon expander means normalized spectral radius is less than or equal to 1 minus epsilon.
Yeah, I got that, but sorry, what is the largest absolute value? Like the largest eigenvalue? What is this?
There is always one eigenvalue which is equal to degree. For example, in this definition, there is an eigenvalue n, which does not satisfy this property.
So my question then is, isn't every graph an epsilon expander as long as the second largest eigenvalue is strictly smaller than the largest one?
Yes.
Okay, but then the statement is that you always need only a constant times a logarithmic number of steps to reach a indistinguishability from uniform.
Yes.
So that's true for every graph then. Or am I misinterpreting?
Like, okay, I think I didn't get the last point. Do you mean, are you asking, are there any graph which is not epsilon expander? Is it your question? No?
Yeah, I guess so. Like, is this really a very non-trivial property, or do you
Yeah, it's
expect?
not. Yeah. I mean, for example, in the definition of my lambda of g, I put this comment if it exists, maybe all eigenvalues are trivial.
Yeah.
Yeah.
So
And
the statement that okay.
And also, when as in the first comparison, what was that? Here, one can say ATY also proved that this graph has rapid mixing property because they found an upper bound for the eigenvalue less than one, you know. So still they can say there is this is an expansion property, so they can still claim rapid mixing property. But then we are not only asking the existence of rapid mixing theory, we are also asking, as Jonathan asked, like how many steps we need. If you use this upper bound, you will get larger value. Does it make sense?
Yeah, I think it makes sense. So the upper bound is really to quantify the constant somehow then.
Do you think the quantifiers were incorrect in my definition?
No, I think I understood the answer. So
Okay.
yeah, I think it's okay. Thank you.
Yeah, okay. Do you have any intuition on whether fluorescence is conjectured lower bound holds? That's a good question. I don't know. Do you have any?
So let me just read the question for the recording. Maher asks, do you have any intuition for whether Florit and Smith's conjectured lower bounds holds? Sorry, just wanted to
Yeah,
have the question in the video.
they should be harder to obtain. Yeah, perhaps they should be harder to obtain. But honestly, I don't see any interesting. I don't see any interest. Like perhaps it is related to my lack of experience on this topic, but why it is really interesting to have some lower bound? Perhaps it is something to say we have the best possible bound or something. I don't know. But honestly, first of all, in that paper, they do two things. First, they computed, especially for the primes until 600s. And then you get that the spectral radius are very close to around 11 and 12. And then they conjectured it seems there is also lower bound. So I don't remember if there is any intuition or any work about the lower bound, if even there is any word about the lower bound in that paper. I don't know. Yeah, welcome.
Are there any other questions? Okay, if not, let's thank Harun again for the talk. And we hope to see you all back in 2 weeks again, where we'll have Edda, who is now, I think, a postdoc at the University of Birmingham. And so, yeah, we hope to see you all back.